Okay, so continuing on with electric field, let me just remind you the definition of electric field. The electric field is defined as the force that a positive test charge will feel. Right? So the sign of the charge Q, remember I have this system where I have a charge Q, and then I have a positive test charge Q naught. The sign of the charge Q determines the direction of the electric field. So for example, if this charge Q is positive, then those two charges are going to be repelled from one another. So I'm going to have a force acting on this charge that's in that direction. That means that the direction of the electric field will also be in that direction. All right? So the direction of the electric field is the same direction because of the way it's defined. It's the same direction of the force that a positive test charge remember this is our charge Q naught, positive test charge, would feel. Well, let's see. So for example here, my positive Q, I'm going to feel a force on my positive test charge in this direction. So my electric field is also in this direction. Now down here I have this positive test charge. It feels a force in this direction towards that charge, and so it feels the electric field is in that direction. Now, if the electric field or if the test charge would go away, so for example, if I had a negative charge, then I would say that the electric field would be in that direction. Right? So my electric field is not really related to the test charge. Right? We just use the test charge as a tool, a thought tool, in order to determine the direction and the magnitude of that electric field. All right. These are vector quantities, so we need to deal with vectors again. So just like we did with the forces, we use the superposition principle to draw the vector. So for example here, I have two charges, Q1 and Q2, and I imagine a positive test charge. So Q1 is going to generate an electric field in this direction. I'll call that E1. Q2 is going to cause an electric field in that direction. I'll call that E2, because that's the direction of the force that a positive test charge would feel. At this point, we just really need to stop drawing this imaginary positive test charge, because, as I said, it's imaginary, it's not a real physical charge. We're just using it as a tool in order to determine the direction of this electric field. So I can draw this then as two vectors, E2 and E1. And then the net electric field is just the vector sum of that. So the net electric field is just going to be E1, which is in the positive x direction, minus E2, which is in the negative x direction. And so, you know, here in this case, if the charges Q1 and Q2 are identical and you're equidistant between them, then the net electric field will equal 0, because E1 would equal E2. Remember, to find the magnitude, define this, but the magnitude is KQ over R squared. So if Q is the same, if they're identical, and they're equidistant between the two charges, so R is the same, R is this distance, then those two vectors would cancel out. So charges can be in 2 or 3 dimensions. We won't see any 3-dimensional problems, but you'll certainly see some 2-dimensional problems. So let's look at this. I want to find the electric field at the center of the cross in this figure. So this is a very similar problem as to what we had before. I just want to first draw my vectors, my E-field vectors. I have E2, which is going to be in this direction. Now, how did I know that it was going to be in that direction? I imagined a positive test charge right there, and I asked myself, what force would that positive test charge feel in response to Q2? And because Q2 is negative, my positive test charge would be attracted to that charge. Now, E1 is going to be in this direction. E1 is in the first quadrant because a positive test charge would be repelled from a positive charge Q1. Or we could find the angles. I'm not going to go through all this. You'll work this in a similar manner. Let's see, should I have any space? Yeah, I'll work through it. If you know how to do this, then please skip on ahead. But let's go ahead and work through this. It's very, very similar to what we did before. Just like we did before, let's go ahead and find this angle. Change colors here. So I want to find this angle. I'll call it theta. So I'm going to draw a little triangle here that can convince you that this angle is the same. All right. So I can find that angle theta is the inverse tan of opposite over adjacent. That's 3 over 4. If I recall, that was 37 degrees. That's correct, right? Yeah, 37 degrees. So that's my angle. Now I need to find my magnitudes, E1 and E2. E1 is KQ over R squared. That's 9 times 10 to the 9th. Q, I'm looking for E1, so Q is 3 times 10 to the minus 9. Divided by R squared. This is 5 meters. That's 5 meters squared. It's coulombs. And now I can find my electric field due to charge number 1. It's 27 over 25. Get 1.08 newtons per coulomb. As I also said, it can be measured in volts per meter. Okay, now I want to find E2 as well. Same way. I'm just finding the magnitudes of the vectors. So the only way this is different from the Coulomb's law problem is because I'm using this different way of finding the magnitude of the vectors. Q2 was 2 nanocoulombs, or 2 times 10 to the minus 9 coulombs, divided by R squared, just 4 meters squared. So let's see, that's 18 divided by 16, 1.125 newtons. Or excuse me, 1.125 newtons per coulomb. Okay, so those are my magnitudes of my vectors. 1.08 at 37 degrees and 1.125. You probably recognize those numbers. They're very similar. I think they're the same except for a scientific, what's it called, the mantissa, the times 10 to the minus 9. Let's redraw this. And this is at 37 degrees. Okay? Let's see, this was E1, and this was E2. The electric field due to charge 1 and the electric field due to charge 2. Okay, so now I want to break my E1 into its X and Y components. I'm going to go ahead and draw them here, but E1 will have a Y component there and an X component here. And so E1X is going to be 1.08 cosine of 37. And E1Y sine of 37. So let's see here. Get 0.8625. Keeping more sig figs than I need. And 0.65. Okay, so those are my X and Y components. And so now, I could redraw this. Now instead of having 2 vectors, I'll have 3 vectors. Okay, now I'm going to combine these 2 vectors I'll say 0.8625 minus 1.125. I get it. I don't think that's right. Yeah, negative 0.2625. I'm just going to call it negative 0.26. And so now I can redraw this again. I get two vectors instead of three because I've combined those two vectors. Here I'm going to have 0.26. I combine those two x components and 0.65. That means that my resultant vector for the electric field will be in this direction. And I want to know this angle. I'll call it phi. Draw a little triangle here. This is 0.26. This is 0.65. And this is E. And I want to know this angle phi. I'm going to go through the same process to find the magnitude and the direction of E. So to find the magnitude of E, we use the Pythagorean theorem. I get 0.49. And then to find phi, the angle phi, I say phi is the inverse tan of opposite over adjacent, 0.65 over 0.26. It's 68 degrees. Okay, so my electric field is 0.49 newtons per coulomb at 68 degrees above the negative x-axis. That's my answer. Very similar to what we have with Coulomb's law problems. Let's see, I think I have some sample problems for you to work through. Let's see, this one's a little bit simpler, or more of a conceptual question, but you should work with this. Here, what we're trying to do is we have two charges that are separated by a distance d, and this point, which is equidistant between the charges, and then at this point, which is d over 2 from the right charge. I want to know where is the electric field the greatest in magnitude. So you want to draw your electric field. I'll do it for point A, but I'm going to leave you to do it for point B. Draw your electric field due to these two. I'm going to call this Q1. I'll call this Q2. And so the electric field due to Q1 is going to be in this direction, right? And the electric field due to Q2 is going to be in this direction, but twice as big because the charge is twice as big. And I'll leave you to do that for side B as well. And I think we'll pause there.